Okay, let me just check if anyone is on the stream now. Okay, should open this beforehand. Okay, can everyone hear me? Okay, because I think I see on the chat that. Okay, can everyone hear me? Okay, because I think I see on the chat that. Okay, can everyone hear me? Okay, because I think I see on the chat that. Okay, can. Okay. I'm also going to hang out in the tutoring room one of the IEEE Discord in case anyone has any questions, or maybe if I'm having some technical issues or anything. You can just message me there or just call me on Discord, I guess. Okay. Okay, just set myself up here and we get started. Okay. So, hi everyone. My name is Simon, and this is the Digital Systems Review. So, hopefully my screen is visible. So, these are the topics that we are going to be going over. So, we're going to start with multiple output circuits and then progress towards decoders, multiplexers, demuxes, and your logic functions as well. Adder blocks, subtractor blocks, tree state buffers, ROM, PLAs, computer architecture, microprocessors, and so on. Okay, so this is okay. So basically, for multiple output circuits, so we have let's say two functions, right? Um, this or this as well. And so, if we were to draw the gate diagrams for these two functions, we can see if we were to implement these functions individually, we would see that this function would be, let's see, so if we have an A, a B here as well, C, and okay, gate. So this would be this, and this as well. This. So, as if we examine these two circuits, we can see that the term A and B, it can be shared between both circuits, right? And so that's just a step in optimization of multiple output circuits. And so I would like to give a much more detailed example. And please, if maybe I'm having some, I don't know, connection issues or whatnot, kindly just message me in the Discord because I had to turn off YouTube just to prevent echoing or anything of the sort. Okay, and so let me just add another page here. Okay, so we have this function, and this is an example for multiple output circuits. So we have this function, right? Um, call this F1. So this should be 10, not a 9. Okay, so let us design the circuits for both functions and see how through optimizations if we can share terms, right? And so if we were to draw the K-map for F1, okay, this would be, I think I will zoom out here just so everything is much clearer. 0, 0, 1, 1, 1. So just tracing the minterms here. So for F1, we have the midterm 0, 1, 6, 13, 15, 10, and 11. 1, and then this is a 1 as well. And then 6, which is 1, 1, 0. Not mistaken, yes. And then we have these four should make up 13, 15, 10, and 11, right? So just the basic K-map simplification here, we can get this get this circle as well, and then this as well. And so we basically see that F1 is just AD plus A bar. Okay, I'm just going to use the bar notation since that's what's prevalent now. A bar, B bar, C bar, and um, that should be A bar, B, C, if I'm not mistaken, and D bar as well. Okay, let me just check. That is correct. That should be the case. Absolutely. Okay. And then for F2, just the same logic. So we just draw the K-map for that as well. we have 0, 0. So drawing this is where we would have that. So we have for 0, we have for 1 as well. Then we also have for 6. And then 14, 15. 14 should be 0 here. And we have 15 is all ones. 12, 13. And am I missing anything here? 14. So it should just be 12. Okay. So again, just the basic K-map simplification here. You can go with these two as well, and then these two as well. And so F2 becomes, so we have AD or BC, correct? Yes. B, C, D bar, and then or AB. So examining these two functions, we can see that AD is common. AD, yes, the term AD is common between both functions, so we can share them. And so if we were to implement this function, we would share these two terms. Okay, but we can even go a step further, but to do that, we would have to simplify in a different order. So, what am I saying here? So, let's say we take out this simplification and then this one as well. Okay. So, and this goes down to the transistor level. So, if we were to count the number of transistors implementing the system such that we share only AD, we would have 62 transistors. Okay, but if we were to implement in a different order, such that okay, let's say we go for this. So we simplify. Okay, give me 1 second. My bad. My bad. I think that was the wrong example. Okay. Okay. So, as already mentioned before, these two terms can be shared, right? But an extra term can be shared as well, and that could reduce the number of three input AND gates that are used. In fact, you wouldn't even need to have a four input AND gate in this case because the term BCD bar can be shared between both systems. So for this circuit here, you would just only have to create BCD bar once, and then you would implement it for F1 such that, okay, let me just draw the circuit implementation so it's much more visible, I guess. Okay, so we have, I think I might have to zoom out of this a little. Okay, I think I ran out of zoom. Okay, okay, so this works. So we have A, B, C, D. I'm just gonna put NOT gates in. It's we have the complement of them. Yeah, we do have A, B, C, D. So for F1, we have A and D, right? A and D, and then A bar, B bar, C bar as well, all of them ended. And then as stated before, we would only need to create B, C, D bar, right? So let's just create that. Let's see. So we have B about here. Okay, I just have to cross those. B, C, and D bar. Okay. So that ended with A bar. So A bar should be about this here. So these three terms ORed together gives us F1, right? And then for F2, we share, so we pick this term, which is AD, if I'm not mistaken. Yes, that should be the case. So AD, and then BCD bar, that has already been implemented. It was implemented here, if I'm not mistaken. So that's BCD bar, yes. So it's here. Okay, it's not working. And AB. So AB, we would have to use an AND gate for that. And then just to draw those beforehand. So we have AB, A, then B as well. So this is, I would say this is an extensive example on optimization of multiple output circuits. And then you have F2 as well. Okay, okay. So let's move on to a different topic. So our next topic is decoders, multiplexers, and demultiplexers. Add another page here. And so for decoders, so basically a decoder is like I would say midterm generator, I guess. And so if, for example, let's consider a 2 by 4 decoder. Okay, so since I haven't gotten any message or anything from Discord, I would like to check the YouTube chat just in case anyone has any inquiries. So just give me a few seconds here. Okay, someone has a question. see. Now the question of the previous example. Let's see. Indeed, you are absolutely correct, Star. I guess I made a mistake on that. Oh my goodness, you are absolutely correct. Okay. I was looking at the wrong one. Oh my goodness, I'm so sorry. You are absolutely correct. Let's just do this again. Oh my goodness. Okay, so for F2, just to resimplify, we have A bar, B bar, and C bar. That's the term we share. My bad, I made a mistake. Okay. And then you have AB as well. So AB is not the term we share. My bad. AB and, or the last term is basically B, C, D bar. So the term we share is A bar, B bar, C bar. A bar, B bar, C bar. So that's the term we share, not AD. So that was a mistake. I'd have to redraw the circuit diagram. So it's A bar, B bar, C bar. That's the term we share. And then, but the simplification still holds because B, C, D bar, it's common between these two as well as A bar, B bar, C bar. Okay, so just to fix this diagram very quickly, I think I already did A bar, B bar, C bar here. Yes, precisely. So we take this one off. Uh, C bar. And AB as well. Do I already have that? Let me check. So BCD bar as well, and then AB. So yes, this should be the correct diagram and the correct simplification as well. Does that make sense? Okay, let's move on. Okay. And so back to decoders. Um, Assuming we have a 2x4 decoder, right? So we have two input lines. I'll just call these I0, I guess. One, and then this is an enable, right? So you would have midterm 0, midterm 1, midterm 2, midterm 3, midterm 3. And then just to draw the truth table, you would have I0 as well. Include enable. So the enable would be 0 in these cases. I'm sorry, my bad. I'm gonna have to redraw all of that again, or better rewrite. Again. Not sure. what the input is. Okay. So for this case, we would have, let's say midterm 3 here, midterm 2 as well, midterm 1, and midterm 0. Okay. So for 0, 0, this would be a 1. 0, 1, this would be a 1. 1, 0, this would be a 1. And 1, 1, this would be a 1. And the rest are zeros. Okay. The rest are zeros. And notice that these outputs are for when the enable is equal to 1. If the enable is equal to 0, we do not even care about the inputs because every output would be 0. And so if we were to draw the circuit diagram for each of these outputs, let's see here, we can clearly see that M0 is basically E times or and I0 bar and I1 bar, right? And then M1 is just notice how it follows the input structure, I guess. So you have I0 bar as well, and then this is just I1 if I'm not mistaken, 0, 1, yeah, okay. And then M2, M3. Okay, so M2 would be this. Okay, so I0, 1, I1 bar. And M3 would just be the enable and, okay, I think I got a message in Discord, I0 and I1. Okay, I have run out of space. Let me just zoom out of this a little bit so I can get more space. And so the gate diagram would basically just be almost in something, this would be something similar. So we have an AND plane and 0, or call it M0. I mistake. 0, 1, 2, 3. And the enable runs through. So we can just do something like this. Connect this here, connect this here, connect this here as well. And we have I0, I1, and your NOT gates. Okay, this should be much lower than it is. If not, the diagram would be incomprehensible. Okay, I just shift it down a bit. Okay, put it around here. So let's say this is I0, so our inputs, I0, I1, I guess, I1, and you have your NOT gates. Okay,
And if you have submitted successfully, you don't need to remain. You don't have to stay on the call. Thank you again for.
okay, sorry for that. Okay, so we have these going through. So this should come this way for the first midterm. And the next one is just I0 bar. So we're going to use this again, and then I1. Okay. Then the next one would just be, yeah, is that correct? Yeah, it is. 1, 0. So the next one would just be this. And okay, this as well. And then the last would be both literals in uncomplemented form. I think I have them here. So this is the gate level schematic of a 2 by 4 decoder. And so decoders are actually very relevant components regarding circuit design. So we can use them to um, implement logical functions as well. So basically, if you have a function, let's just say a random, let's see if I have a specific example here. Okay, okay. In fact, let me just give, I think I have the problems laid out already. Okay, very good. So I do not know if this is completely visible, but okay, we have this. So use the fewest number of 2 by 4 decoders and gates to implement a 3-bit incrementer. Okay. 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 So we're using the fewest number of 2 by 4 decoders and gates to implement a 3-bit incrementer. Sorry, to implement a 3-bit incrementer. This circuit should accept a 3-bit integer and produce set integer plus 1 as output. So basically, we just want to design this function using only decoders and, if possible, the fewest amount of gates as well. So a 3-bit incrementer, right? So we would have 3 inputs. So A, B, and C. And so we're going to have 8 possible combinations, correct? So we have this as well. Okay. So okay. So since we're incrementing each input by 1, the maximum possible output would be 9 because we're gonna have 8 plus 1, which is 9, and 9 would be represent can be represented as 4 bits. So basically, our output should comprise 4 bits. So I can just just call this D3, D2, D1, and D0. Okay. So for this, so if we add 1 to 0, we get 1. Add 1 to 1, we get 2. So this is basically just like the next combination for each of the inputs, right? So if we add 1 to 2, we get 3. And this is 4, 5, 6, 7. Wait a second, hold on. Did I miss something here? Mm, yeah, then this would be, And then this should be 8, correct? Okay. Okay. And now to design the, now we just have to design the circuit. So for this, since we have three inputs, we would basically have to not directly use, but since we have to use 2x4 decoders, we would have to decompose a 3x8 decoder into two 2x4 decoders. So at best, we should be working with two 2x4 decoders. So let me just quickly show how to convert a 3x8 decoder into two 2x4 decoders. Yes. So a 3x8 decoder, right? Okay, let me just quickly draw the truth table for that. I would have to do it all the way. Okay, let me zoom out. Okay, so there's space. Okay, so okay. So now notice that for this set of combinations, A stays at 0 throughout, right? And then you have the same repetitive sequence. So you have 0001, 1011. And then that repeats in the next set of combinations as well. So that's I'd say the giveaway that you can use a decode two 2x4 decoders for this. So basically you would have one decoder with an enable and then another as well. So normally you could just okay, let's not get ahead of ourselves. So we have that. And then for A, we just have a NOT gate, right? So if A is 0, the NOT gate converts that to a 1, and then the first decoder is activated, whilst the second would be deactivated because the enable would be 0. So in this case, you would have BC, and then BC as well. And then for this, you would have min term 0. So I'm just going to put an extra column for our truth table. Min term, so this would be min term 0, min term 1, min term 2, 3, 4, 5, yeah, and 7. Okay. So for the first four outputs, those should give us the first four minterms. And please, if anyone has any questions, I'm currently looking at the chat, so yeah, feel free to ask any questions through the chats. Okay. And then the second decoder should give us the last four minterms as well. So you have M4, M5, okay, M6, and oh my goodness, M7. Okay, so basically, instead of using a 3x8 decoder, you can use two 2x4 decoders to, yeah, you can use those instead. And also, 4x16 decoder as well, that could be broken down into two 3x8 decoders. But I'm not going to do that now. So it's the same logic. You can definitely apply it. Okay, so back to our problem. we have the truth table for incrementer. All that we have to do now the is just to draw get the circuits, right? But first of all, notice that for these three outputs, okay, so for D3, we can see that the only one we have is for this midterm. Okay. And then D2 as well, we have ones for these four midterms, correct? So basically for these functions, instead of using gates, that is, instead of drawing the K-map to know what gates to use, we can just use two 2x4 decoders to obtain the outputs, the function for these three outputs. But notice that D0, I can just quickly draw the K-map for that. D0 is basically C bar, right? So instead of using a decoder for that, we can just use a NOT gate. So, okay, what is wrong with precisely? D0 is C bar, so we can just implement that. Um, yeah, we can just implement that directly using a NOT gate. So to complete the circuit, we have, so we're going to need two 2x4 decoders. Okay, so we know the most significant bits. All we need to do is just pick M7. Here we have this is D3. And then for D2, so we just pick midterm 1, 2, 3, 4, 5, 6. So midterms 3 to 6. 3 to 6. And we put a massive OR gate, and that is D2. Okay. And so D1 would just be midterms 1 and 2. Okay, no questions yet. So midterms 1 and 2 and 5 and 6. Okay, go away. Midterms 1 and 2 and 5 and 6. Did I do that correctly? Yeah. And we put another OR gate, and this is D1. So basically, designing logic functions using decoders, it comprises just identifying the minterms and ORing, that is, feeding those minterms as inputs to an OR gate. Okay, so let us move on to multiplexer. Okay, so before we answer or work on this problem, let us examine multiplexers. So what are multiplexers? Okay, let me just add this on a separate page so that we have space for said problem. Okay, let me make this 2 to the k since it's technically. So basically for multiplexers, we have some inputs and we have respective select lines. So the select lines determine what input goes through to the output, right? So let's say, for example, we have a 2 by 1 multiplexer. Okay, so something like this. And then we would just need one select line. So the select lines can be obtained by taking the logarithm of the inputs. So log to the base of 2, right? So let's see. Uh, inputs. So like the cardinality of select lines equals log to the 2 of inputs. So since we just have two inputs, okay, let me we have a B, and then this is just call this S0. So what is the truth table? Okay. 0 is 0, F is A. If 0 is 1, F is B. So yeah, that's pretty much it for muxes. And they're very useful components as well. We would be working on a processor design problem, and muxes will show up again. So definitely keep them in mind. And so another good, I would say, benefit of muxes is that they are um, universal components, such that the NOT gate, AND gate, and OR gate can be derived from a 2 by 1 specifically a 2 by 1 multiplexer. Okay, let me show how that's the case. So we have for a knot. So we want to show that F equals a bar. So we put A here. Okay. So from the equation of a mux, we have that A bar times 1 plus A and A is 0, right? So anything like 0 is basically 0, right? So we have just A bar and 1 or 0, and that's just A bar. So basically, this configuration, it gives us, let's see here, the knots for a 2 by 1 mux. Okay, so for an OR, that is a bit, I wouldn't say complex, but it's a bit more involved. So we want to show that F is A or B. Okay, so we have something like this, right? So F is here, we have A here, we have B, and we have 1, right? Okay, so F equals A bar and B or A. But that's not A or B, right? Well, using the OR distributive property, you would see that this is A or A bar and, okay, this is not writing, A or B. Okay, so A or A bar is 1, right? So this is just a 1. And finally, we have A or B, which was what we wanted to prove. Okay, so let's try the last one, the AND. This one should be much more straightforward. For the AND, we're trying to prove that F is A and B. Okay, so this is F, this is A. Okay, so we just put a B here, and we put a 0 here. Okay, so F equals, okay, A bar and 0 or A and B. Okay, so this is 0, and then you have 0 or some term, which is that term itself. So we have A and B. So basically, the mux can be used to replace each of the, I would say, the atomic gates. So the and, the not, and the OR gate as well. Okay. Let me see if there's anything else. Okay. So now I think we should be ready to work on the problem. So we have the majority function. It's equal to 1 when 2 or 3 of its arguments equal 1. So basically, we need to implement this circuit using just one 2 by 1 mux and the smallest number of extra gates. Okay, so let's just draw the truth table for this. Basically, the ones of these functions of this function are for each combination where we have greater than or equal to two ones. Okay. Okay. So implementing this with so let's write the function. Let's also see if there are any simplifications using a K-map. So we're just going to have to try to simplify as much as possible since because we're limited to just a 2 by 1 mux. So we're just going to have to simplify as much as possible. Okay. Okay, nice. Okay. So where was it bar? Or let's see here. So it should be XY as well. One second here. Yeah. So we have Y bar Z. Okay, not bar. So it should be a YZ. Okay. YZ, XZ. Yes, correct. And XY as well. Yes, that is the case. XY. Okay. So from this, just looking at the function, we can see that yeah, it would be difficult to implement this using the 2 by 1 mux directly. But if we examined this function here, okay, then I do that. Hold on a second. So if we examine the original function, we can see that. Give me one second. Okay, so we have x bar. Okay. This is going back to the original function. So I'm just going to pick x as our select line, right? So we have that. and y bar z or yz bar or yz. If I'm not mistaken. Let's see. Yeah, okay. Okay. Or z. And then we can also see that we can simplify the expression that we have within this parentheses. So if we duplicated this term, we should be able to do some Boolean algebra here and successfully implement this using just a 2 by 1 mux. So for these two, factor out a z, you have a y bar or a y. Okay. And then for this as well, so for these two, if you, let's see, it's common. So we can factor out a y if I'm not mistaken. Yes, yeah. Then you have a z or z bar. Okay. So at the end, we have that x bar, yz, or x, and since this is a 1, this is a 1, y or z. Okay. So, now we can draw f. Okay. Right. And then if we use x as our select line, so for that, we're just going to have an AND gate, and then y and z, right? And for here, we would have an OR gate. Okay, that was a very bad OR gate. Okay, like, and y or z. And that is our function. So we were able to implement the function using just one 2 by 1 mux and the smallest number of extra gates. And so we can see that for this function specifically, simplifying using the K-map didn't actually help. I guess it didn't actually help. So the main thing to notice when designing functions using muxes is just to first of all look for the term that um, appears in most of the min terms. So in this case, we can see that x, y, z they appear, pretty much throughout. So that's that's not a good criteria. But we can see that for x, well, I would say maybe it was a lucky guess, but well, yeah. So we can also see that we have x bar. At least that covers this term, and then x covers these three terms, and so you can just factor out um, x itself and then the complemented x as well, and then you have the expression that we had here. So basically, this method is called Shannon's expansion. So the formal definition for Shannon's expansion, I do not think you guys were taught this in your class, in Dr. Nikoubin's class, but I'll just briefly introduce this here. Okay, so we have this is called Shannon's expansion. So the formal definition is basically something like this. You have x1, so multiple variables, and then you have xi, and then just multiple variables. So this is just xi bar, right? And give me 1 second. There is no one here. And so basically what this means is just pick a variable, preferably a good variable like x in this case for our function. Pick a variable and then set that variable to 0. Whatever resulting function you get, multiply that function by the complement of the variable you picked. Or, and then you add your or, and then that same variable, and set that variable to 1 in the original function, and um, literal itself and the resultant function that you get. So basically, if we come back to our function here, since we picked x, if we set x to 0, we see that, okay, yeah, we set x to 0, this becomes a 1, so you have y, z, and then this is just 0, 0, 0. So basically everything goes away, and then we have this first term, okay? And then if we set x to 1, this goes to 0, yes. And then you have just y bar z, yz bar, and yz, which is what we add here. And then you can even continue the process again, maybe picking y or z here. And yeah, basically, you just keep breaking the function or keep decomposing the function until you have it in the form where it lends itself to a 2 by 1 mux or whatever mux that you're trying to use. Okay, so let me just draw the timing diagram, just explain the timing diagram related to muxes. I think that was okay. Let's say for example we have 4 by 1 mux. Okay, we have A, B, and we have these inputs. So let's draw the timing diagram. And let's label the input such that this is I0, and then this is I12, this should be I3, yes, I3. Okay. Um, Star, are you referring to Shannon's expansion? Okay. Okay. I will as I will assume that you're talking about Shannon's expansion. Okay. Yeah, so let's say we have a this. Okay. So I'm just gonna draw some lines here just for better representation so we do not confuse ourselves. So we this is a one, this is a zero, this is a zero. Okay. So basically, if A is zero and B is zero, what would be Y, right? So Y would be, okay, I'm just gonna also add this here. Y would be I zero. Okay. And then if A is one and B is zero, that corresponds to input two or I2, and that is a one. So we would have a high here, okay, and this would be I2, okay. And then we have that these two, this is 1, 1. So A is 1, B is 1, and that should give us a low as well for I3. So we can see this is relatively straightforward. And then this repeats again. So we have A is 1, B is 0. And so we just get a high as well. Okay, that's that. Okay, and so we considered muxes. Let's consider demultiplexers. So I would say demultiplexers are more or less for theoretical interest. You would rarely, in fact, well, don't quote me on this, but you would most definitely not use those components physically or even for design problems. But that's just at least know what they are. So for a demultiplexer, let's say it's basically just the inverse of a mux, I guess. That's what you want to call it. Then you also have select lines again. So I'm just going to use a technically, don't know if this exists, but a 1 by 4 demultiplexer. Okay, so you have this right here. So, let's see, call this 0. Doesn't matter, D1, D2. So we have S1 and S0. Okay, so basically, the true table for this is something of the like, okay, okay, just confirm that I should look at the chat more often. Okay, star, got you. Okay, please, if anyone has any questions, I'm currently looking at the chat. Just feel free to type it in. Any questions? Any maybe I made a mistake or something? Please feel free to um, talk. Okay, so you have 0, 0, 0, 1, 1, 0, 1, 1. Right? So for a demultiplexer, oh, I also forgot to talk about encoders, but I do not think you guys. Hmm, I'll briefly mention that as well. Okay. So this is, and so what this device does is based on the select inputs, it matches. So just imagine like you have something like this, right? So based on the select inputs, it routes Z, whatever Z is, to each of those outputs. So that is a demultiplexer. Okay, let's see what we can do here. See if we can do an extra problem on 8 by 1 boxes. Give me 1 second. Okay. Okay. Let's work one more problem on muxes, and we would progress to, let's see, adders. Okay, just one more problem. Here. Okay, nice. So we have this function. Um, First of all, I'm just going to draw the 8 by 1 mux. Okay, so basically, to implement this function, we're going to have to use a heuristic. Just bear with me here. Okay, so let's say we have this, right? I would reverse the order just to make it make sense for you guys. Zero. And I would like to preface that this method, yeah, it's definitely, like I said, it's a heuristic, so it's definitely not the best when approaching design problems. regarding muxes. Let me check the chat again in case anyone has any question. Okay, nobody yet. Sounds good. Okay. Okay. 0, 1. Just call this, or better yet, 2, 4, 5, by 6, by 7. Just bear with me. Hopefully everything would make sense at the very end. Okay, so we have a bar and a. So for all zeros, let's see, does that give us a 1? Yes, so this would be 0. So basically all that we do is to write the min terms, quote unquote, for each cell in this table that we have. Oh, I wrote a bar twice. All right. Okay, so this is like 0, this is 1, and then 1, 0, 0, 0, that is 8. So we have 8 as well. And then this would just be 1. Okay, now I see why it should have been rotated. Okay, okay. Can definitely do better. Okay. I apologize, but I will have to clean this just to make the diagram more comprehensible. Okay, so better to put B here, C, D, right? So basically all we're trying to do is to write the resultant minterms in each cell of the table that we have below. Okay. So this would be 0, 0, 0. This should be 0, 0, 1. So it goes from like this, bottom to top. And then we have 0, 1, 0, 0, 1, 1, 1, 0, 0, yes, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So same logic applies. So we just write out the resultant minterms. This would be 1, 0, 0, 1, which is 9, and then so on and so forth. So 8, 9, 10, 11, 12, 13, 14, 15. So now basically what we do is to see if one column is represented in our function. If that's the case, if it's either, so I would say you're more or less grouping the column like a term. So if it's represented in the function, if both of them are represented in the function, then you just write a 1. So, oh, I forgot to add this here. Then you would just write a 1 for the input. If both of them are not, you would represent that as a 0 for the input. But if one or the other, then it's either A or A bar. But we'll see. We'll get there. So we see 0 and 8. So I'll just put a check there. 1 and 9, absolutely. Let's see here. And remember, for the don't cares, you can regard them as a 0 or 1. So in this case, we do not have 2. And I'm just going to regard this 10 as a 0. So that's next. Let's see, 3 and 11. So that could be 0 or 1. Don't care. So don't care. Okay. Let me use a better notation. So for this, I will put ah, okay. Just put 0. That's much better. So, and then we leave the x for the 1. So this is a 1, a 1. And then 4 and 12, 1 as well. 5 and 13, 1 as well. Let's see. So we have 15. Okay. Let's see if anyone has any questions. Okay, not yet. We have 15, but we do not have 7. 6 and 14, we do not have any of those. That's 0 as well. Okay, so just to backtrack, let's see. We have 0, 8. We have 1, 9. 2, 10. No, we do not have either. 3, 11. Well, don't care, so literally don't care. And then 4, 12. Yes. 5, 13. Yes. 6, 14. No. And 15, we just have 1. So what we're going to do is to fill in these. So we have 1, 1, 0. Don't care. Could be either. Doesn't matter. Then for 12, 1, 1, 0. Whilst for this, you would have to represent this as an A. As an A. Since we're only covering one term, we do not cover both. So we would have to represent this as A for the inputs. And yeah, this is the function using just one 8 by 1 mux. Okay. Okay. So now let us progress to adders. Okay, just give me 1 second. So for adders, you're going to consider two components, quote unquote. They are the half adder and full adder. Okay. So first of all, how does addition work in binary, right? So we have A, B, consider them as inputs, and then you have a carry and a sum. Nice. Okay. So same stuff for regarding truth table. Just draw your so 0 plus 0, that's 0. No carry, no sum. Or no, sum is 0. Then 0, 1, no carry, sum is 1. Then for 1, 0, you have sum is 1 as well, no carry. And then 1, 1, the sum is 0, and you have a carry of 1, right? So a device that performs this operation on 2 bits is called the half adder. So it's usually represented like this, right? So you have half adder. And please feel free to ask questions. I haven't gotten any question yet in the chat. Okay. So you have a half adder. This represents the inputs, and then you have a sum and a carry. So now notice that this sum can be represented as an XOR function, right? So it's basically just A XOR B, right? So you have like 0, 0 gives you 0, 1, 1 gives you 0, 0, 1 gives you 1, 1, 0 gives you 1. Okay? And now notice that the carry is basically just A and B. So this column here is basically A and B. So within this block of abstraction that we have here, A and B, you have something like this. I'm just going to make it much more bigger so you guys can see. S, and then you have this XOR A, B. That's the sum. Then you have an AND gate, which is the carry. Okay. But now there is another device. It's called the full adder. And this is the more practical device because this is what is used in adder blocks. So you have S again, and then now we distinguish between the carries. So this term, the one on the left-hand side, is called the carry in, and then the other is called the carry out. So now we have an extra input. So we have to redraw our truth table. Okay. So you have carry out and sum. Let me just quickly look at the chat if anyone has it. Okay, no questions yet. So it's basically the same thing. The first four should be the same as the half adder in terms of the truth table. So um, mhm, I missed the one. Okay, so for carry out, no carry, no carry. So for the first three, we shouldn't have any carry until the fourth. So this should be 0, it should be 1, 1, just like the previous truth table, and this is 0. Okay. While for this, you have an extra. So now you consider these three terms as a sum. So for this case, we do not have any carry, but we have the sum being 1 because you have 1 plus 0 plus 0. Now for this case, you have a carry as well because you have 1 plus 0 plus 1. So that's 2, 1, 0 in binary, and the sum is 0. And then the same applies for this term as well. You have 1 and then 0. And then the last, you have 1 and the sum is 1. So we have our full adder. Okay. And so to obtain 4 bits, 5 bits, whatever number of bits adders, right? All we do is just to concatenate multiple full adders. Okay. So for example, if we wanted to get, okay, let's say a 3-bit adder, right? So 3-bit adder. So you have one full adder. Okay, Einstein is not writing. And then a second one as well. Then the last one. Remember, each full adder has 3 inputs, right? So in this case, you would partition the bits of each input since it's a 3-bit adder. So this would be like the least significant bit for both inputs here. So this would be B0. And then this would be the subsequent bits, B1 and B2 as well. Okay. And then remember we had a carry in, right? So initially the carry in is going to be 0 because literally this is, the first two sums that you're taking, right? And then we have a sum and then we have a carry out. But we're not going to display this carry out. It's going to come into the second full adder as an input. So that's where the concatenation comes in. Okay. So we have this, and then this comes here as well. Okay. And then you have your sum and your C out. So this is a 3-bit adder system. And then you could abstract away these details by, doing something like this, right? So you just have C0. Okay, I'll call this S0, S1, S2, S1, oh sorry, S2, S1, and S0. And then for this, you would have, you know, A0 and so on and so forth, right? Or you could use a notation in which, okay, okay. Yeah, so you can use a notation 3 represents multiple lines, and then you just call this A, call this B. And then the same applies for the output as well. So you can take these out. Yeah, just a power of abstractions, I guess. So 3 and sum. And this is your 3-bit adder. And now notice that you could concatenate this 3-bit adder with another 3-bit adder to get maybe a 6-bit adder, and so on and so forth, right? So notice that this 3-bit adder looks okay. Did I miss something here? Yeah, I did. I missed the carry in, the initial carry in. Okay, which would be 0 for our purposes. But yeah, so you can concatenate this with multiple. Notice that it looks quite similar to the full adder. So you can concatenate this with multiple other adders to get different adder blocks, I guess. Okay, so we've looked at addition. What about subtraction? So there are two different ways of performing subtraction in binary. So you could use the direct method where you borrow, but that is very confusing and easy to, I would say, make a mistake or whatnot. Hence, why there is a different method. So the different method is called two's complement, I guess, or called using the two's complements. Two's complements. So basically, A minus B, where A is a binary number and B is a binary number as well, equals A plus B bar plus 1. Now you might ask, how does this work? Okay, let's just try it on two numbers. Let's say A equals 8, right? In binary. That is, yeah. And then B equals, let's say, 5 in binary. That gives us what? Mhm. So we want to perform A minus B, which we know is 3 in binary. Okay, so what do we do first? So, well, first of all, we perform the two's complement on B. So I think this is called, okay, no, sorry. There's usually a term for each term, the term that you're subtracting from. Don't worry about that. It's not important now. So if you take the complement of this, we'd have 1, 0, 1, 0. And then if you add 1, you get 1, 0, 1, 1. Okay, so now we add this term to 8, and we should get 3 if the method is correct. Okay, so you have this. So if we add, we get this, right? But in most cases, you ignore this this carry, right? In some cases it's a 1, some cases it's a 0, but just ignore the carry. It's not important. And yeah, indeed, we do get 3. So that's a straightforward method for doing subtraction, right? And now, with that being said, we can um, basically contrive a subtractor block from an adder block. How come? Well, notice that subtraction now is basically addition. Instead, all that we're doing is just negating the, the subtracting term and just adding 1. Okay, so let's go back to our 3-bit adder. Or let's make it a 4-bit, right? So we know that 3 bits, 4 bits. So let's say we have this right here, right? So we have, let's see, we have C out. Okay, let me see if I have any questions in the chat. Okay, nobody yet. So we have C out, S3, S2, S1, and S0. Okay, then we have the carry in as well. Okay. So what do we do? Well, we have first of all, we're expecting 4 bits, right? I said it's a 4-bit adder, so we are expecting 4 bits. A0, A1, A2, and A3. But now we're just going to add not gates here, right? Not gates. And yeah, this is basically a subtractor block, right? Yeah. But we can do better because why convert an adder to a subtractor block when you could, okay, yeah, when you could um, make one device that can perform both operations, let's say based on some signal, right? Okay, or some input. So instead, instead of this setup that we have here, what we could do is instead of we could do something of the like. So let's say we have something like this. Okay, I'm probably gonna have to shift this below because I would need more space. Okay, trying to draw an XOR gate there. That did not work now, did it? Okay, let me. Yeah, I'm definitely gonna need more space than I thought. Or I could just draw smaller gates. Give me 1 second. Okay, so they don't really look like XOR gates, but those are XOR gates. Okay, and so you let's say we have a signal, right, called some input X, whatever it is. Okay, so this feeds into each of the XOR gates, right? And then we would also have mhm, each bit from our second input number. So we have I'm just gonna call this B3. Yeah, so B3, B2, B1, B0. Now, why does this work? Why an XOR gate? Well, because the XOR function is defined this way. So A bar B plus B bar A. Okay. So now notice that we want X. If X is 1, right? That is X our signal here. If it's 1, we want the complement of B. Basically, we want all the bits of B to be complemented. And if X is 0, we want B to be as is. Okay? So let's try those two cases with the XOR function that we have here and see what happens. So let's assume A is A and, sorry. Let's assume that this is some input and this is our X of interest, right? So we have A XOR, 0, right? What do you have? Well, we have B, right? So this is B, and then this is just or 0, right? This is B, okay? And then if we try A XOR 1, right? Using the same function here, so what do we get? Well, let's see. Give me 1 second first. Okay, I think. Oh, no, 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 no. My bad. My bad. Mix them up. Okay, let's do that again. Okay, so we get A, not B. We get A. I'm very sorry. We get A. And then AX are 1. So if B is 1, what do we get? Well, this should give us a bar, right? Yeah, that kind of it works. It works. So if X is 1, we have a subtractor. And if X is 0, we have an adder. So you can call this a 4-bit full adder. That, that makes sense. Okay, so now with this, we can also obtain what's it called? From a subtractor, we can obtain a comparator, and I will show why in 1 second. Okay. So you have S0, S1, S2, and S3. Okay. Then you have C as well. Okay. So I'm just gonna use the previous schematic that we used for the subtractor. So you have a one here, and then you have NOT gates. So I just represent them as bubbles. Okay, so you have your B input here. So B3, B2, B1, B0, A0, A1, A2, and A3. Okay, so now notice that, remember this is a subtractor. Notice that A minus B, if this equals 0, okay, that implies that A equals B, right? Yeah, it does. So what do? Well, we basically just OR all of these inputs. Let's say put them into an OR gate. I'm just going to put a slash here, put a 4 to represent that using the previous notation. Put that into an OR gate, and you negate that value as well. And that tells you if A is equal to B. Yeah, it does. So, for example, right, if we get all zeros, the OR gate gives us a 0 as output. Negate that, and you get a 1. If you get any of them as a 1, the OR gate gives you a 1. Negate that, you get a 0. So A is not equal to B. And now the carry. Well, the carry is it's a very useful tool, or I guess a useful, I don't know, phenomenon, or whatever you want to say. So let's just try some examples, right? So A equals 8, right? B equals 3. I think we already did that here. Let me check if we have that. And you can try this for, I guess, any input pair where A, which is the first bit, is greater than or equal to. Second bit, if I'm not mistaken. Yeah, you would get a 1 here as a carry. But if A is lesser than B, the carry would be a 0. Okay, so I think we've already done the case of where A is greater. So let's try a different case. Let's get a negative number. Let's see what happens, right? So just using the two's complements again, let's say A equals 3, B equals 5, right? So we converted this to binary. We would have 1, this is 0, 1, 0, 1. And then if we perform the two's complement on this, right? Okay. 0, 1, 0, 1, bar, and plus 1. Okay. Okay. So for this, we have 1, 0. I think we did this before. 1, 0, 1, 0, and then plus 1, if I'm not mistaken, yeah. So you just flip them. So 1, 0, 1, 1. Okay, let's add. So you have 0, 0, 1, 1 plus 1, 0, 1, 1. So we have 0, so 1 here, 1 here, and then 1. And guess what? The carry is 0. So yeah, basically, yeah, whenever you have this is, hold on 1 second. Yeah, I forgot to mention whenever you're performing two's complement and your result is a negative number, you don't get the result directly. You have to perform two's complement again before you get the actual result. So like for this, if we perform two's complement, that is if I did my addition correctly, we should get 0, 0, 0, 1, and then if you add 1, you get surprisingly 0, 0. Remember, we always ignore the carry, right? So 0, 0, 1, 0, which is, guess what? 2. So yeah, 3 minus 5, negative 2. Okay. So yeah, basically for the carry, yeah. So for the carry, whenever we have 0, that corresponds to A lesser than or equal to B. Okay. Okay, let me just wipe some of this stuff here so we have some space. Okay, give me 1 second. So let's try one more case. A equals B, just for good measure. Okay. So if it performs two's complement on this as well, that should yield 1, 0, 1, just for good measure. So 0, 0, 1, 1 plus 1, 0, 1. So we have 1, so that's 0, 1. Okay. So now notice that we get 0, right? So notice that we get 1 when A is greater than B and when A is equal to B. So we know that if the carry is 0, right? Carry is 0, it implies that A is lesser than B, right? But now, since we already deduced how to get A equals B from the sum inputs, all we have to do is just set up an or AND gate here, right? Set up an AND gate and then just connect your this as an input into the AND gate. So we know that if A equals B is 1 and C is 1 as well, it means certainly, give me 1 second, it wouldn't have to be the OR gates. It would be this inputs. Because if you connect the OR gates, then yeah, that defeats the purpose. So that wouldn't work. Well, yeah, is the direct the input here. So basically, if we get remember that for this, if we get a 0 as the output, it means that A is equal to B, right? So even if this was a 1 and this is a 0, it means that A is not greater than B because A is equal to B. But if that's not the case, that is, if we had a 1 from this and we had that A is greater than B, um, yeah, so that should give us the desired output that we're looking for. And then to get A lesser than B, all we have to do is just negate the inputs directly. So if we negate that, we just get A lesser than B because we're certain that if the carry is 0, A is most definitely lesser than B. So if you negate that, you get 1, and yeah. So we have successfully built a um, comparator using a subtractor. Okay, so now let us move on to three state buffers. This here. Okay, before I continue, I would like to. Okay, just give me 1 second, everyone. C4. Okay, wasn't there also not on the C4? A less than B. I think I included that star, or didn't I? Let's see. Are you talking about this NOT gate? Yeah, I, I included that NOT gate. Okay, okay, so let's go to three state buffers. Alrighty. Mhm. Okay. Mhm. Okay. Okay, so just give me 1 or 2 minutes, everyone. I will be right back. Okay, I am back. So regarding the tri-state buffer, okay, what I'm going to do directly after this is to show the application of this tri-state buffer and buffers in general in a register file. Okay, so we have this set up. Let me check if anyone has any questions. Okay, no, not yet. So we have this set up for a tri-state buffer. So if B, right? If okay, let me just draw the truth table first of all. Yeah, let's put B first. B is a one. B is a one. A, the input is basically passed as the output for this case. So this case is called the active high tri-state buffer. Active high tri-state buffer. Okay. And then, like I said, but if B is zero, it doesn't matter what A is. So I'm just going to put a don't care, because we literally do not care. You have a state called Z, where C is this state Z represents high impedance. So yeah, that's all there is to it for a tri-state buffer. And then we have, I would say, variations of this. So you can have another type called active high inversion, inverting tri-state buffer. So all of the following variations that I'll list, it's just okay. All right, the diagram should give the details. So this high in the or this qualifier high for the variation, it basically means that if B is one, you get the tri-state buffer. If B is zero, you get the high impedance case, right? But then the inverting qualifier basically means it just signifies if you have inversion of the input as for the output or not. So in this case, we have an inversion. So let's call this C, right? So truth table again, right? So this is 1, 1. This is 0, 1. And in this case, you have inversion, right? And then if this is 0, doesn't even matter what X is, you get high impedance, okay? And then the third variation is active low tri-state buffer, right? Let's one notice. So let's see. How does that look like? So it's basically something like this, right? This. So you have A and B. So what's the truth table? Well, okay. Up again. So B, A, C, right? So if B is 0, B is 0, you have A. So input is passed as output and stuff. Now, if B is 1, doesn't matter what A is, you get high impedance. That's for the active low tri-state buffer. Yes. And then the last variation is active low inverting tri-state buffer. So for this, the diagram is this. A, B, and you have a bubble as well here. See? Okay. So this is basically basically it's like this, but C is just A inverted, right? So the tri-state buffer can be used to or tri-state buffer or I'll say a combination of tri-state buffers can give you the and the or function. Well, for the knots, we basically know that this is what we have here. Give me 1 second. Yeah, this one. So this is kind of like the knots, as long as B is 1. Or this one here, as long as B is 0. Okay, so what combination yields an AND? Well, consider this setup. So we have something like this, right? Mm, let's say we have some input A. This input is 0, and then F. So now notice that we're combining two outputs to yield F. So with that being said, it's not possible for you to get, um, I would say, a coherent value if the outputs of both buffers they differ. If that makes sense. Like if you have, let's say, an output here is 1, right, and this is 0, we don't know what F is. If that makes sense, right? Okay. So basically, with that being said, what we would have to do is if our control signal here, if we wanted to reuse that control signal for this buffer, we would have to negate that signal. Okay. So now, what is F? So let's consider if B is 0, right? If B is 0, you have high impedance here, and you have what? You have 1, because this is 1, so you have 0 here. So for this, we know most definitely that if B is 0, we get a 0, because this is high impedance, right? So high impedance basically means like nothing is coming from there, but then we have a 0 going through, right? So current takes the path of least resistance. You literally have like, almost infinite resistance here, so current is not going to take that path. Yeah, we have that. So what about if B is 1? Well, if B is 1, we have that this is 0 and then A goes through. Well, this is basically F equals AB. Yeah, that's pretty much it. Because if B is 1, you have F as A. If B is 0, you have F as 0. If B is 0. Okay. So this combination yields A and B. Okay, let's consider a different combination. Okay, so for this, well, let's check what happens if B is 0. So if B is 0, we have A. So if B is 0, we have A. And then if B is 1, we have 1. Well, that's literally A or B, right? Because if B is 0, you just have A, right? And then if B is 1 as well, you just have 1. Because 1 or anything is 1. Okay. And you can try this as an exercise on your own, or you could just check Google or something. um, how would you get XOR as a combination of two tri-state buffers? Just try it. Seems like should be a good exercise. Okay, so now we've considered the theory behind tri-state buffers. Let us work an example. Give me 1 second here. I hope this works. Okay, let us try this. Okay. Okay, so this schematic is for a register file, the register file of a processor. And so, before we proceed, I would need to give a specific, um, I would say, assembly instruction. So let's say we have, and I'm just going to pivot. So from this topic, I will also pivot to the topics that we're supposed to cover involving microprocessors and so on. So I think, yeah. So basically this, and then once we're done, we might work one problem involving tracing bits on the microprocessor, and then we round up with ROMs and PLAs. Okay. Okay. Let's see. Do I still have that? Okay, I have it here. So I'm just gonna write the okay, I literally do not have any space here, but I'll just try my best. So I'll write the instruction that we have up here. So this is a subtraction, right? We have two registers, T2, T1, and T0. And please, please, please feel free to ask me any questions. Okay. Okay, so if we're converting this to the machine code, let me just pull up something very quickly. So you can use this, right? So this instruction here, it falls under this category. So up here, oh, I think I did this prior. Give me 1 second. Okay, yes, I did this here. Absolutely. So you have opcode, RS, which is the source register, RT, which is your, let me just call it temporary register, and then RD, which is destination register, right? And then shift. For our purposes, shift is always 0, so like 50 bits. And then you have function, right, which is outlined here. So basically, you get your function code in this case, which is represented as a hexadecimal value, and you get your register bits as well, and that should give you your what's it called? Machine code. So remember that we had, okay, I'm just going to write the instruction here, and then we obtain our machine code, and then we go back to the register file diagram. So we had subtract T2, okay, T4, no, T1, not T4, T1, 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 and then T0, right? So according to this, we need our option code, operation code, opcode or operation code. So sub is basically all zeros. So you're just gonna have, and remember that in converting hexadecimal to binary, all you have to do is to take each digit of the hexadecimal value and convert that to binary. So in this case, we have Well, it has to be four, so 4 bits. Each hexadecimal value or digit represents 4 bits in binary. And then the next one as well. But now notice that we have 8 bits, and the opcode here needs to be 6 bits. So what we do is we always truncate. So we obviate the first 2 bits, and then we just have a total of 6. Yeah, 1, 2, 3, 4, 5, 6. Yeah, 6. So we have 6 bits. Feel free to ask me any questions. This, or if I'm going too fast, you can always stop me. Okay. 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 So we have source register. So in this case, how the subtraction works is that T2 equals T1 minus T0. I'm not mistaken, that is the case. 1 second. Indeed, that is the case. And so, yeah, so in that case, this would be our RS. So T1 is our RS, this is our RT, and then this is our RD. Okay. So we write, so from here we can see that RS is just, these are the addresses, right? So let's see, T1 is 9 as the address. So the opcode would be 01001. Yes, that should be the case. And then T0, so that would just be 01000. Okay. And then we have the shift, which I think I stated before. It's all zeros for our purposes. And then you have the function code. So for sub, let's see, the function code is 22. So remember, in converting hexadecimal to binary, you have this, right? And then this again. This is 22 in binary, like, sorry, yeah, 22 in from hexadecimal to binary. And remember, we obviate the first 2 bits, and we just have and this. And yeah, so this is our machine code. Awesome. Okay, so coming back to here, I am just going to probably split my screen here just to make it look much better so that I don't have to rewrite everything again. Okay, so all that is important from the machine code is the last 3 bits of RS, RT, because those are the addresses for this decoder. So remember, this example culminates, I think, all that we've done so far regarding tri-state buffers and decoders. So these components are called registers. So we can just forget about those for now. So you have RT, right? So all you need for RT are the last 3 bits. So in this case, our R3 we can write 000, right? Because this is RT. And then our S, the source register. Remember, okay, I would need to do this. Oh no, this I guess. Okay, that is not working as I expected. Okay. Oh, okay, I can just scroll on this. Okay. So remember, RSRT. So this one would just be 001. And then for R2, that is the right address. That would be 010. Okay. So basically what we're doing is we are following the processor. So this is what happens when this operation is being performed by the processor. It fills in these bits into these I would say not fields technically, but like these wires, they get these bits, and then these wires get these bits as inputs as well, and then everything just follows. So for this, we know most definitely that the enable has to be 1 because we are writing into a register. Okay. And then write data as well. So basically, this is the content that we're going to write into the register. So in this case, it would be the content of T1 yes minus content of T0. So all of this should be inside here. Okay. And then this is the contents of RS, which we know to be T1, contents of T1. This would be the contents of T0. Okay. Now, remember that for decoders, if you're for decoders, if you get a certain combination of inputs, it basically corresponds to a specific minterm. So in this case, our minterm would be D2. Yes, if you remember, yeah, it would be D2. And then all of these would be 0. 0, 0, 0, 0, 0. If anyone has any questions in the chat, okay, none. And we have these are tri-state buffers. So what they do is that they control this bus line. This is a bus line, right? So literally, one tri-state buffer drives the bus. So how does that happen? Well, okay, give me 1 second. It depends on the address for this decoder. So notice that the minterms for this decoder, they're connected to the enable inputs or the select inputs for enable inputs for the tri-state buffer. So in this case, we would have that this would be a 1, and then the rest would be 0. So basically, you would have high impedance on every other bus except the bus that has D1 as its enable input. So literally, this tri-state buffer drives this bus line. And how does that happen? So basically, notice that, remember, we said RS is T register T1. So by all means, the contents of T1 should be in this bus line. So notice how if you trace this, you can see that this goes like this, and then it goes into this buffer, and then it sees, oh, this is a 1. And then literally it dumps its contents into this bus, and we have this, which we said was the contents of T1. Nice. So same logic applies here as well. So this would be a 1. Every other tri-state buffer be 0. And notice that these are just buffers, not tri-state buffers. This is another component. I do not think you guys were taught this, but yeah, what these components do, they just pass signals. So there's no select line or whatever, or enable. It's just they pass signals, or more or less they amplify them. Okay, and so you have 0, 0, 0, 0. Okay, and the same logic applies. So notice that this goes like this. But remember, this was a 0, so it's not dumping its content into the bus. And then if you trace this node as well, comes all the way here. And ooh, this is a 1. And then it dumps its contents. And yeah, we have this. And now, how does this um, subtraction value, how does it get written into T2? Well, let's trace. So you have the input coming this way, right? And then it goes this way, like this, like this. Oh, and then notice that this output always goes into every register, but only the register that has a load. So this symbol here represents the clock. Only the register that has a load as 1 would receive or absorb the value, I guess. So for other registers with 0, their contents don't change. So this register, yeah, it changes its contents to reflect this subtraction. So hopefully this example was, I would say, illustrative for applications of decoders and tri-state buffers as well. Because one thing is to learn theory and another is to see its practical application. So let me just pull up one more regarding processor design, and then we move on to ROMs and PLAs. So I'm just going to work um, one simple example. This should cover addition, right? Addition. Yeah. So addition and subtractions are, they're quite similar in terms of machine code, but they have their differences, as you would expect. Okay, let's see. Give me 1 second here. Okay, this. So basically, what we're going to do with this example is to trace or walk what happens in the processor in one clock cycle. Okay. Okay. So first of all, the same logic applies regarding getting the function code, which we did here for the subtraction, right? So all you have to do is for the addition, you would just use let's see, use a different op. Oh, let's see, it's the same opcode if I'm not mistaken. Is there? Yeah, it's the same opcode, so that doesn't change. But then you just appropriately replace the destination register, source register, RT, and remember, shift for our purposes, they're all zeros. And then for the function code, let's see what we have. Okay, yeah. So for the function code for add, it's a bit different. So I'm just gonna write that as well. And yeah, then I'll just give you guys the machine code. So remember conversion from hexadecimal to binary. You have 0010 and then 0, all zeros. Yeah, very good. And remember, we always, disregard the first 2 bits, and this would just be our function code. Very nice. Okay, so if we come back here, I'm just going to write the machine code, and we very quickly walk through what happens in a processor. Okay, so remember this is our S, so RS for our case is T5, and then this is T4, RT, and you have destination register, and then you have shift, and remember the last 6 bits, which corresponds to the function code. Okay, so so let's start from the leftmost part of the diagram, right? So we have instruction memory. So this instruction memory, it feeds these 32 bits. So notice how you have IR. So this is from 31. 31 is the leftmost bit or most significant, and then 0 represents the least significant. So what we can do is just partition accordingly. So we have 31. I'm just going to put 26 here, 25, and then put a 21 here. This should be 20, and then 16, 15, 11. This is a 10, and we get, let's see, uh, this is a 6, and then this runs from 5 to 0. Okay, so basically, it says 31 to 26. Those bits, which we know to be 5 zeros, they come here. They go to this control unit. Okay, and now 25 to 21, remember that is our S. And lo and behold, we have that those bits going to our S. So we have 0, 1, 1, 0, 1. And now 20 to 16, those bits go to our T. 0, 1, 1, 0, 0. Well, now notice that that input also goes into this mux. So remember when we talked about muxes? Yep, they have come back. So what I'm going to do is just apply some um, logic here so it makes sense. So you have that input here, and then 15 to 11, you have these bits, which is our D. So now notice that we know that T6 is the destination register. So by all means, get after after whatever happens to this mux, by all means, RD should equal 0, 1, 1, 1, 0. So basically, this input must be routed to the output of this mux. For that to happen, this control line, this red line you see here, it's what they call it. It should carry the signal 1. And that abbreviation, if that's what I'm going to call it, it means register file write address select. Right. So basically, what it's saying is we are writing, right? We are writing some data into the register block. Hence, the select line, should be a 1. Okay, so this would be a 1. So remember, we're just walking through how the processor, executes this instruction. Okay, so moving forward, this read data 1 is basically the contents of RS. Remember, I think we did that here, correct? Yes, here. So it's basically the contents of RS, and then this is the contents of RT. So this is read data 1, this is read data 2 here. Okay. And then this one as well. So this register block, right? This block of abstraction is its internals is this. This. Okay. So now this 32-bit wire, it carries the contents of RS, which we know to be T5. And then this one as well carries the contents of T4. And you will notice that I disregarded these bits here. These are only relevant when you're dealing with instructions that have immediates, like add immediate, some jumps, I guess. Yeah, but that's not the case here. So let's disregard that. And load word and store word as well. Okay. So notice that inputs, right? It comes to this mux. And then the input that I just told you to disregard also goes into this mux as well. So by all means, we know that the output of this mux here, it should be the contents of T4. So just reverse engineering that inference, we know that, or by all means, the select line for this mux should be a 1. So this is a 1. So basically, as you can see, and I'll assume, I think your professor might have given you, or maybe in your textbook or something, you will notice that there is I would take a boilerplate set of conditionals that give out these control lines. But instead of memorizing that, you can just basically deduce each of the control line yourself, just using this process, right? Okay. So so this is the ALU, right? It's called the arithmetic logic unit. So it performs addition, subtraction, comparisons, and whatever. In this case, we're dealing with addition, right? So this ALU control also has, let's see here. So for this, I'm just going to put FC, right? FC. And here, add. We can technically disregard this, but I'm just going to put it there for to make it more clear. So now we have the contents of the ALU here, which would be, I'll just call it sum, right? So this sum represents contents of T5 plus the contents of T4. Okay. Okay. So notice that that sum goes into this block here, data memory, right? And then it also goes into this mux here. So this data memory is only useful for two instructions, load word and store word. So for this case, we're not doing either, hence the 0 zeros for these control lines, right? In general, all of these red lines, they're usually bear a 0 or 1. Okay, 0 or 1. So, that being said, we know that we have sum here. So we have sum going into this mux, and for all purposes, I would say, garbage going into this mux because we don't know what's coming out of data memory. We literally did not, we're not expecting anything. So, yeah. So we know that the sum needs to go through this wire and go all the way here to be written into T6. So for that to happen, this select line has to be a 1. And voila, we're done. We're basically done. Let me add something here. So yeah, and so once this mux receives the 1 as a select line, if anyone has any questions. Okay, nobody yet. Yeah, so it routes sum all the way to this register block, which we have here. And then what we talked about before happens, where you have load, which is dictated by the input of this decoder, and then that gets into the register and so on. Okay, I hope everything is making sense. So yeah, I hope it makes sense. Okay, so we are done with this, and processor design was a quick rundown, but that's all we have. Okay, so let's proceed to ROM and PLAs. Okay, so what is a ROM? What is a ROM? Okay, so a ROM is usually of this form. So I'm just going to give you an example. This is an 8x4 ROM. This 8 represents the words or address line. And we're going to work one problem involving ROM design. Okay. So these address lines are basically the outputs of this decoder. So this right here is a 3x8 decoder. And then from this, you should be able to deduce the general case for ROMs. So we have this this, 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 1, 2, 3, 4, 5, 6, 7, 8. And now you could, and then this is called a memory array. The memory array is basically a truth table. Yeah, that's pretty much it. So it's a truth table. A truth table for um, it could be numerous functions, right? So it could be, so in this case, let's imagine we have three functions, right? F1, F2, F3. And then for, okay, let's just expand on this truth table a bit. So it's going to have, so the truth table, it's, I would say its number of rows are dependent on the address lines, right? So you can literally only, address what address is available, if that makes sense. So let's say, we have 8 of these rows, right? And then three functions. So this would be F1, F2, and F3. And that is pretty much what a ROM is. Okay. 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 Give me 1 second. Yeah, that is pretty much what a ROM is. And then you could abstract away most of these details. That's if you notice, that's like the recurring theme for digital logic abstractions. So let's call this, and then remember we just have these two, and we just have our give me 1 second, our 8 by 4 ROM, and then this is F1, F2, F3. Yeah, and that is it. Okay, let us work a problem on ROM. Okay. Let me expand or highlight this. Just give me 1 second. Okay, so we are to implement the following logic function with two outputs, P and Q, using one or more of the following ROMs, right? 4 by 1, 4 by 2, 8 by 1, 8 by 2, 16 by 1, 16 by 2. Okay, so first of all, let's examine the functions that we have, right? And normally, one would be inclined to draw maybe to try simplifying the functions, but yeah, simplification in some cases, especially for design problems that have certain constraints, simplification is usually not the way to go. Give me 1 second. Okay. Like in our case, we're constrained to use specific types of ROMs. Okay. So P is W, and the apostrophe on each of the literals, it's you can replace that with bars. Yeah. I'm sure that's what you guys are more familiar with. So we have this, okay, then V bar, Z bar, and or VZ. Okay. So notice that we can simplify this just using Boolean algebra, right? Okay. So this is a 1, and we have WX bar or V bar, Z bar, or VZ. Now, we are in luck because this term can be represented by one ROM. This can be represented by, and specifically, let's see, a 4 by 1 ROM, yeah? 4 by 1 ROM. This as well. can be represented by a 4 by 1. Yeah, 4 by 1. So these are just midterms, midterms and combination of midterms. Okay. So if that's the case, then, and also okay, I'm just going to give you guys a specific or a much better representation of ROMs. That's helpful for design problems. W next. So what you could do is you could represent the memory array, right? Represent the memory array instead of just the blank box. You can represent the memory array. So in this case, you would have so you can represent, let's say, just convention, right? This is the first midterm, second midterm, and so on. So this would be 0 because for our purposes, we want this. Well, let's call it F1 should equal W X bar, right? So what midterm is that? That's the second midterm, right? Yeah, so this would be 0, this would be 1, this would be 0. Okay, make sense? Okay. And moving forward, let's get the second, because I said this could be implemented by a 4 by 1 ROM as well. Okay, so you have V, Z. Remember, we're representing the memory array on the ROM. Okay, so you have this right here, and yeah, basically this is midterm 0, this is midterm 1. So this is an XNOR function, if I'm not mistaken. It's an XNOR function. Yeah. So you can implement that as a ROM as well. And yeah, we have F2, which equals, I'm just going to write V XNOR Z, yes, and just put a bar. Yeah, yeah. Okay, so now we're not done yet because we need a OR these two. So these two, they would come in as inputs into another ROM. Okay, and it will be a 4 by 1. So this at the end should give us P. So this is probably something that, yeah. So also you can use a ROM to represent any function, not and or XOR X whatever. You can use a ROM to represent any function. So it's a universal component like the what's it called? 2 by 1 muxes as well, and also NAND gates and NOR gates. So for this, remember it's an OR, right? So OR, remember we're you know using convention like 0 midterm and whatever. So this would be 1, this would be 1, this would be 1. So this ROM is basically F1 or F2, and that is just P. Okay. And yeah. So remember that there was an extra constraint, right? So our design should use the least number of memory bits. And remember, to get the number of memory bits for a ROM, all you have to do is just multiply the title of the ROM, more or less. So if you have like an 8 by 4 ROM, oh, was that a whatever? Yeah, have like a 4 by 1 ROM, 8 by 3 ROM, 8 by 4 ROM. The number of bits it would basically be for 8 by 4 it would be 32 because you have 8 times 4. And then 4 times 1 for a 4 by 1 ROM, 4 times 2 for a 4 by 2 ROM, and so on and so forth. Okay. So let's work on Q. Let's see. And the approach to Q would would most definitely be a counterintuitive approach. Give me 1 second. Okay. Okay. So for Q, we have this. Now, notice that we can rewrite Q as something like this, right? But if we implemented Q directly like this, we would have to use how many? We would have to use three 4x1 ROMs, right? So we would have to use a 4x1 ROM to implement X bar, Y bar. We have to use a 4x1 ROM to implement Y and Z. And then we have to use another 4x1 ROM to implement the OR of both of them. So that's total of how many bits? That's already 12 bits. Can we do better? Most definitely. Okay, let's see what we can do. Give me 1 second. Okay. So what we can do is to expand these terms, right? So notice that this, and remember, Q is a function of four variables, W, X, Y, Z. So notice that this variable, we can rewrite this as something like this, right? Okay. And then this one can be rewritten as something like this. So this is kind of counterintuitive because usually we want to go from an unsimplified form to a simplified form whenever we're dealing with, design, whatever. But in this case, we're going backwards, so it's kind of counterintuitive. Okay. And then if we, expand those, we get something like this. Okay. 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 So we have this, right? And now notice that W is common in each of these terms. So we can factor out W, right? So remember, this, what's it called? If we had implemented the function like this, we would have used 12 bits just for the terms within the parentheses. And then we would also have to AND that with a W as well. So that's an extra 4 bits. So that's a total of about 16 bits. Let's see if our implementation now would give us something lesser than 16 bits. Yeah. So if you factor out a W, you have X bar, Y bar, Z bar, or X bar, Y bar, Z, or X, Y, Z, or X bar, Y, Z. Okay. So now notice that these terms, they're basically min terms of some combination of X, Y, and Z, right? They're basically min terms. So what we can do is that all of this can be done by one 8x1 ROM, which is very nice. So we've basically gone from having 12 bits here to 8 bits. Awesome. Okay, so let's implement that function. So we have X, Y, and Z, right? And then you have your 8 rows, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we have this one's a 1. Okay. And give me 1 second. X, Y, Y. So we have 0, 0, 1 as well. Yeah, so this is a 1. And then all ones. Yeah, so it's the last midterm. 1 as well. And then this one is 0, 1, 1. So that's 3. Yes, I'm not mistaken. Yeah. So the rest is zeros. Nice. So now all we have to do is to AND this with W. So imagine you had W here, and you feed that into another ROM, and this should give us Q. So remember, AND is just 0, 0, 0, 1. And yeah, basically in total we have 12 bits for the whole system as opposed to having 16 bits. So we saved a total of 4 bits, which is nice. And yeah, in total you have 12 bits here, 12 bits here. So that's 24 bits. Yeah, okay. So let us move on to PLA, programmable logic arrays. Okay, okay. So the general structure for PLA, it's kind of similar to a ROM, but different components, right? So you have two planes or two arrays for PLA. These are called programmable logic arrays. Okay. So this just means like ad infinitum, like multiple of these lengths. So you have n input lines, okay? And then this is our AND array or AND plane and our OR array as well, okay? Difference is this is not a decoder. This is not a decoder because it doesn't generate all of the minterms. Doesn't even generate midterms. It depends on. That's why it's programmable. So you can I would say choose what terms you would love to generate, or design them or whatever. And then yeah, you can have multiple of these as well, depending on your purpose. Okay. And then you have output lines as well. So M output lines. Okay. Okay. So let me just give a quick example. All right. Quick example of a PLA. Mhm. So this is called the AND plane. This is called the OR plane. I'm going to remove these for now. Oh, well, put it here. OR plane. And these are OR gates. So these are, okay. So basically you have every, input, I guess. Let me shift the C to the left a bit so we have more space, I guess. So we have C here, and then this as well. Yeah. And then for the PLAs, you create you program your connections. So let's say you have this, output, whatever, and then let's say you create a connection here, right? Or here. And thing about PLAs, you can have these AND gates, they can basically bear multiple inputs. Like you could have an extra or something of the sort, that just depends. But then when we consider PLAs that the AND gates can take in multiple inputs, we do not necessarily draw out the input lines. So it's usually of the form where you just have one line, right? And then you have like some X's representing the connections within the plane, and you just have like one input. Because I mean, drawing multiple lines, that's, you know, gets unwieldy very fast. Okay, so for this as well, let's say you just wanted to connect. So this function would be A bar and B. Okay. And for this, let's say we just wanted C. Why not? C. And then for this, let's say we wanted C bar and B bar. All right, so B bar and C. Sorry, didn't have to draw that. B bar, C bar. And let's see here. This we just wanted B bar. Why not? And this we just wanted B. Okay, so B and B bar. Okay. And then these wires would run through this OR plane. Okay. And you would have OR gates that are proportional or not proportional, equivalent to the number of outputs that you desire. So in this case, let's say we wanted just two outputs, right? Two outputs. It would be more. I would say it would be much more efficient if for the I would say the end I would say the values or basically the terms that are generated from the end plane. It's more efficient if your OR plane is utilizing at least one instance of these terms. If you're not, then why did you create it? No. Okay. So let me scroll down a bit here. You can just do like three outputs, right? Okay. So this one would be, let's say, B or B bar and BC bar. Okay. And then for this, let's say we have B or C. Okay. And then same, you would have connections here indicating, yeah, these. And then for these as well. Okay. And then for this, let's say we just wanted A bar or C. So basically, we ended up with, let's call this F0, F1, F2. Okay. So if you're drawing the quote unquote the truth table, quote unquote, for the PLA, it's something of the like. So you have input ABC since that's what we had, and then outputs F0, F1, do. So we have product term. So for product term, we have one, two, three, four, five, five product terms. Okay. Okay. And so A bar B, right? So this was a zero. We picked a zero. We didn't touch C. So see, this is a one. We didn't touch A. We didn't touch B. And then the same applies. Zero, zero. Disregard A. Then B, we have a zero. Disregard A. Disregard C. One. Disregard A. Disregard C. Okay. Okay. So for the outputs, let's see here. So if I have zero, B bars will one for that. B bar, C bar, my bad. And then B bar as well. And then B, and then these two are zeros. Okay. Mm, Okay. And then for F1, we have C, so 1, and then B, 1, and then the rest are just zeros. And then F2, A bar B, and then C, and then the rest are zeros. Okay. So that is your programmable logic array. And it's ensuing truth table. Okay. Let's see. Yeah, we have successfully covered all of our topics. So, any questions? Any questions? Does anyone have any questions? Any questions? Absolutely. Thank you very much, Kevin. Thank you for attending. Thank you. I'll just hang around for a few minutes in case anyone has any questions. If you could personally message me on Discord if you do not want your question to show up on the YouTube chat. So there's that. I'll just hang around for a bit in case anyone has any questions. Let me even check my Discord. I don't think I had it open. Oh my goodness. Okay. Any questions? Okay. Yeah, Star. Thank you very much for attending as well. I was gonna say what I need to know. I mean, if you're particularly iffy on any topic, you can just throw it out. You don't have to specifically ask a question, but just any topic at all. Then I can just quickly go over it again, I guess. So yeah, feel free, feel free. Any doubts or whatever. Any questions, anyone? Any questions on any of these topics at all? So, if you feel iffy on any topic, I know it was a lot. It was absolutely a lot. So, if anyone feels iffy on any topic, they can just, I think, identify or just say something and, yeah, we can quickly go over it. It might help someone else, even if it doesn't help you. It might help someone else. So, any questions? Any questions, especially about the processor design? Because I think I might have gone a bit overboard on that. But yeah, it was definitely a very relevant question as it combined decoders, tri-state buffers, and muxes as well. So it was most definitely yeah. Okay, it seems there are no questions. I would be ending the session. Thanks everyone for showing up. Um, have a good one. Bye.